Welcome to our tutorial on forecasting with ARIMA models. In this session, we will take a deep dive into time series analysis and how we can apply ARIMA models effectively using Java. First, let's discuss what ARIMA stands for. ARIMA is an acronym for Autoregressive Integrated Moving Average. It is a popular statistical method used for time series forecasting. What makes ARIMA powerful is its ability to capture various aspects of time series data. Before we start with the coding, let's break down the components of ARIMA. ARIMA has three main components: AR, autoregressive, I, integrated, and MA, moving average. The AR part refers to the relationship between an observation and a number of lagged observations, previous time points. The I part refers to the use of differencing the raw observations to allow for the time series to become stationary. Lastly, the MA part refers to the relationship between an observation and a residual error from a moving average model. Now, let's get into setting up our Java environment. For this, we'll be using the statistical Java library, known as JStat. First, ensure you have JStat included in your project dependencies. If you are using Maven, you can add it to your pom.xml as follows. In this tutorial, we will begin with a sample dataset. Let's simulate some time series data to work with. Here's a simple piece of code to create a synthetic time series dataset. In this code snippet, we have created a method called generateData that simulates a sine wave with some random noise added to it. The array holds 100 data points that we will use for our forecasting experiments. Now that we have our data, the next step is to visualize it, to understand the behavior of our time series visually. To do this, we can use a basic plotting library such as JFreeChart. Here's how you can create a line chart for our generated data. In this code, we created a method called plot that takes a double array as input, representing the time series data. We used the JFreeChart library to create a line chart that visualizes our data. Now that we can visualize our data, we need to check its stationarity. A stationary time series is one whose statistical properties do not change over time. There are different statistical tests to check for stationarity, like the augmented Dickey-Fuller test. In our case, we can simply inspect the plot first, but for a more rigorous approach, we typically would implement a Dickey-Fuller test. Note that implementing a Dickey-Fuller test from scratch can be complex, but libraries can sometimes help. Now, let's start constructing our ARIMA model. In this segment of the tutorial, we will implement the core calculations of the ARIMA model using the generated time series data. We need to identify values for P, D, and Q, where P is the number of lag observations, AR term. D is the number of times that the raw observations are differenced. Q is the size of the moving average window, MA term. For our example, let's start with P equals 1, D equals 1, and Q equals 1. Which can be adjusted later based on the ACF and PACF plots. We'll create a method to apply the ARIMA model using these parameters. This code represents a skeleton for our ARIMA model. The fit method is where we will implement the fitting logic. In practice, this can be quite complex, and often libraries like Apache Commons Math or others can help with the underlying calculations. Next, we need to implement the differencing operation, which helps us transform our data into a stationary series. We will create a simple method that applies differencing to our dataset. In this code snippet, the difference method takes in an array of data and returns a new array where each element is the difference between consecutive elements. This will help us achieve stationarity. Now, the next essential step is fitting the AR and MA parts of our model. This will involve creating the corresponding matrices for the AR and MA coefficients. For simplicity, we will use a simple estimation technique to initialize these coefficients. Here we have placeholders for estimating AR and MA coefficients. In real applications, you should compute these coefficients using appropriate methods like ordinary least squares, OLS, for AR and maximum likelihood estimation, MLE, for MA coefficients. Next, we also need to consider how to predict future values with our fitted ARIMA model. This process involves using our model's parameters to forecast upcoming time series points based on previous observations. In the predict function, we have a placeholder for generating future predictions based on our fitted model. The actual calculation logic will depend on how you compute AR and MA predictions. Additionally, we must account for model evaluation. A common practice is to split our time series data into training and testing subsets. We'll create a method to evaluate forecast accuracy using measures like mean absolute error, MAE, or mean squared error, MSE. In this evaluation method, we compute the mean squared error based on actual and forecasted values, allowing us to assess our model's performance quantitatively. Now, let's summarize the process we followed for implementing an ARIMA model in Java. First, we discussed the theoretical background and constructed a synthetic time series. Next, we visualized it and set up the foundational classes to apply the ARIMA methodology. We implemented differencing to achieve stationarity, estimated parameters for AR and MA components, developed a prediction mechanism, and set up an evaluation technique to measure forecast accuracy. Lastly, it's important to stress that ARIMA modeling can get quite complex, and while we provided a foundational understanding and basic implementation, you may benefit from using dedicated libraries or tools specialized for this purpose in production environments. Thank you for joining me in this tutorial on forecasting with ARIMA models using Java. I hope you found it insightful and feel inspired to dive deeper into time series analysis.